Dr. Ming Shui. Dr. Ming Shui got his bachelor's degree from the Nanjing University, China, and PhD degree from the University of Reading, UK, both in meteorology. He is currently the Weather News Chair Professor, George Lynn Cross Research Professor at School of Meteorology, and Director of the Center for Analysis and Prediction at University of Oklahoma. His research interests cover several areas. Some of them are data assimilation techniques and systems, regional model and physics development and evaluation, radar meteorology and applications, mesoscale and convective scale dynamics and prediction, and air quality modeling and regional climate systems. Climate simulations. So he is a prolific publisher. He published around 300 papers in the referred journals. The title of his talk for today is, I think I have two different titles, but anyway, the title, it shows development and testing of data assimilation and ensemble forecasting capabilities at CAPS for a unified forecast system. With that, Dr. Ming Shui, the floor is yours.
Okay, Chandra, thanks for the introduction. Today, on behalf of CAP scientists and also NOAA collaborators, I'm going to report on some of the recent work and I guess past 2 or 3 years work on the data assimilation, mainly inside the GSI data assimilation system, and working with initially WRF and then now FE3. And also some real-time forecasting work we did for the HWT and HMT test beds, again, mostly using the FA3 model. And part of the work and DA, especially DA work, will be supported by the JTTI and then also the test bed grants, and then also one on forecast grant. And then I listed some of the collaborators and not complete. Here's the outline. So first, I'm going to briefly discuss the issues with the radar data assimilation and also what is being done in the operational models currently, and then talk about the radar DA capabilities we implemented within the GSI framework, using EnKF and then EN3DVAR methods, and then show some test results, and then summarize and with the extended testing at GSL with our collaborators on the JTTI project, testing the system or capability over 1 month period, and summarize with the scores, and also briefly mention the lightning data assimilation that we're doing within GSI. It's a GOES-R lightning data DA, and then some very preliminary results analyzing reflectivity in the JTTI framework. And then also the real-time testing work for the 2 test beds. So it's a lot of stuff. We know currently the RAP has been assimilating reflectivity data for over a decade, and mainly using the cloud analysis method and combined with digital filter initialization. And then the HRRR, and I think the LAM also has such capabilities. So radar reflectivity mainly go into the system through the cloud analysis, and it's a latent heating derived from reflectivity that kind of gave most impact or benefits. At CAPS, we have been working on radar DA for a long time, and a practical method we have been using in the HWT, HMT real-time test is the 3DVAR cloud analysis method, and we have been testing over counters since 2008. And of course, we're also working extensively with EnKF and EnVar, with our own DA system at CAPS, and also more recent years with the GSI. We know the HRRR version 4 that's going to into operation, that's being tested at the GSL, it combines the EnKF. It uses the GSI EN3DVAR, but it combines it with a EnKF based HRRR system. So it has a HRRR EnKF system, and it uses the mean and then perturbations to feed into the 3DVAR But right now, it does not assimilate reflectivity directly. It still uses cloud analysis, and other data are using the EM3D-VAR method. And this is the version that's going to, the last implementation of HRRR. And then one on forecast mostly has been using EnKF, and then there's some method with the EnVar method. Yeah, we know that all the operational systems, the GFS, and then the next generation, the RRFS, plan to use the hybrid method and then hopefully combined with the self-consistent Ensemble DA system. And because of that, and we do want to be able to directly assimilate radar data within the hybrid framework. Assimilating radar data in EnKF is relatively more straightforward, and there are more issues assimilating, especially reflectivity, in a hybrid framework. And so our work has been mainly supported by JTTI and one on forecast, developing EnKF and EnVar capabilities within the GSI framework, and testing it with initially WRF and then now more with the FX-ray and LAM regional. And then we have done retrospective testing and then also real time at the GSL. Briefly mentioned the JTTI work. This is a lot of details, and basically for reflectivity assimilation in the variational framework, there are a lot of issues, especially mainly because of the operator is very nonlinear, and when it's very nonlinear, the gradient can reach infinity when your background value is very small, and then also can create discontinuity, and also the cost function term associated with the reflectivity data can become very large. The gradient of that can become very large, so that it dominates the gradient term, entire gradient term, and making the assimilation of other data like radial velocity data ineffective. So if we directly use mixing ratios of hydrometers as control variables, we run into these problems. And the only solution we can find is if we still use mixing ratios, we have to assimilate reflectivity data and other data separately in separate steps. And so that's theoretically is somewhat problematic. There are some other work, it's mainly Shuguang Wang's group, and they propose to use reflectivity directly as control variable instead of the hydrometers. And this does avoid the operator appearing in the cost function, but then your background term on the static background covariance, if you want to include it in hybrid system, then you have to rely on statistical correlations instead of using the operators directly. So we would like to be able to use the Z operator directly, and the Z operator is consistent with microphysics schemes. So basically try to still stick to the traditional hybrid system with both static and then ensemble covariance. So our solution is to use either log of mixing ratios or some kind of power transform of hydrometer variables instead of the mixing ratios themselves. And we find that seems to solve most of the problems, although still there are some issues that we still have to do special treatment. And then we do need to be concerned with the reflectivity operator being consistent with microphysics scheme used in the prediction model. So it's kind of a background, and then this is just quickly, if you have single moment scheme and reflectivity, the operators look like this, and mainly they are functioning of mixing ratios, just mixing ratios, and there are log and exponential functions involved. If you use double moment scheme, and then it's a function of both mixing ratio and number concentration. If you use triple moment, then your data assimilation has to really analyze both the mixing ratio and the number concentration. Yeah, so we're proposing, actually this is the idea originally from the Jim Purcell, using this power transform for the mixing ratio and the number concentration, and then this exponent p changes between 0 and 1, and then given this different value of p, actually the transform function varies somewhat like the linear function and then the nonlinear function. This end p equal to 0 actually approaches log function. So we tested log function as well as the power transform, and then in the end we are using this one because it's very flexible, and then you can tune your p to achieve what you desire. But still, even okay, say initially we tested log log of mixing ratio as the control variable. And when you do that, you solve most of the problems, but you still have some issues of generating like the spurious reflectivity. Here is the OC data, so we know the truths. Initially, we test with OC, and then and these are spurious, and mainly the outside of the main reflectivity core, it can generate these spurious ones. And after some special techniques and to deal with them and treatment, and then we kind of can avoid those spurious reflectivity increments. So after testing this with the OC data published in this paper, and then now we applied it to the GSI EnKF system, and this is applying to a real case where we tested the P changing from 0 to 1, and then we see that since a 0.4 P value gives generally the best the ETS scores for different threshold. You see the thick black lines has the highest scores. And also we do see that if you use mixing ratio directly, the convergence is much slower than if you use the either log or power function. So you see that if you use these, and then the reduction of cost function is very quick, fast, and then just within the first 10 iterations, and while the mixing ratio is much slower and actually too slow. Yeah, it's the same case that the end result of applying this say power transform or log, and then we obtain this is the supercell tornadic supercell case, and then the updraft helicity forecast over 3 hours the tracks of them, and with like a power function with 0.4, we see these tracks actually agree pretty well with the observed tornado reports. Why the using Q itself, not only it's a slow in iterations, and also they end up with results that's less not as good as the other transform. So these are implemented within the GSI and tested for a case, and this is with the Wolf model. So that result is with Wolf model, and then more recently we work more with the FE3 model, initially called SAR FE3, and say first test with the relative smaller domain. Again, this tornadic supercell case, and comparing. And within the hybrid EnVar, you can if you set the ensemble covariance to 0, use completely 100% static covariance, then it's really a 3D VAR. And or you use 100% ensemble covariance, then it's a pure EN3D VAR, and or you combine them, it's hybrid. And then the EnVar does need a EnKF to provide the perturbation. So EnKF itself is a complete DA system, so you can just use EnKF only. So we can compare these relative performance for this case. And this is published in GRL. We believe it's probably the first paper applying GSI direct radar DA with FE3 and comparing the different case results. And this is simply show that during the assimilation cycles, this is with 15-minute cycles, we see like 3D VAR, it actually produced the tightest fit of the analysis to observe the reflectivity. Basically, the error level is lowest, but because it doesn't produce consistent analysis of all the other variables, so the forecast error grow the fastest because they just don't have consistent say temperature, moisture analysis. So forecast error grow fastest. While EnKF and then the hybrid or other EnVar, even though the analysis don't fit as tightly, but the error growth is much slower, and that's actually what you desire. You wanted the forecast error to be lower, and this is for reflectivity and then radial velocity. And it's mainly show that the 3D VAR, the red is the worst, and it does not, even for radial velocity, it does not produce the as good analysis or forecast. And yeah, so what for this case, it's a tornadic case, but it involves into a really this observation involved into a line or more linear convective system. And we show the forecast for up to 4 hours at EnKF and then 3D VAR versus hybrid. And we see that there's some old prediction of reflectivity, but generally it's able to 4 hours still maintain or produce this the intense score line. And this study, when it was done, the operation operator, reflectivity operator, was still using the Lin-based scheme, and then while the forecast was using Thompson. So there's some inconsistency, and then part of that, the over-predicting reflectivity is due to the Lin scheme used, even though that, we did publish the paper. And the scores, ETS scores for the rain, and then we see generally 3D-VAR doesn't produce, even though 3D-VAR produce very tight fit in the analysis of reflectivity, but its clear score drops very quickly because the imbalances, while the say hybrid or EnKF, and they also have pretty good fit initially, and then they maintain the clear score, let's say, over this 4 hours, and the performance diagram and also show the 3D-VAR is generally the worst, and why the others are more similar, and then with some performance, some like the pure EN 3D-VAR performs maybe, and then the EnKF probably perform the best in some, at some time, some forecast length hours. And then if you look at the neighborhood probability of the, say, maximum UH within this time period, and we see the hybrid EN 3D-VAR generally produce the probability pattern that matches best with the observed severe storm reports, while the 3D-VAR is missing this part. And overall, these the pure EnVar and 3D or hybrid or EnKF, more or less they produce the high probability within this cluster of tornado and another reports. So I would consider they are generally successful, and compared to 3D-VAR. 3D-VAR is okay, but not as good. So that's the applying this these methods into a small domain, and testing with FE3. That's SAR FE3 was still called, and then more recently, and we applied it to this 4 corner 3-kilometer grid. It's like HRRR type of grid, and we use the HRRR physics configurations. Basically, we're kind of aiming at HRRR, and then so we can compare with HRRR, and so use a consistent Thompson reflectivity operator, and then it's using power transform or mixing ratios as well as number concentration, because Thompson is 2 moment, partially 2 moment, so it has number concentration. Basic number concentration is also an analyzed field in the DA. It's in terms of the power transform, and of course afterwards you have to convert it back to the original quantities. So for this, the LAM applied to the 4 corner 3-kilometer grid, and for 12 hours forecast and 24-hour forecast, we see this case of score line. Actually, forecast is I would say it's actually very good in terms of location, and then somewhat some difference in the intensity. For 24 hours forecast, I'll consider it very good. If you do neighborhood, the probability neighborhood ETS scores, it should give you pretty good scores. Let's keep jumping already. So those are tests with individual or retrospective tests with cases. We have a lot more cases and handy. So those are just examples, but the more importantly is to apply the capabilities in a quasar operational environment. That's part of our the JTTI project task. And actually, it's a collaborative project with the GSL, where the Jeff Duda took our codes and then run it actually over 2 months period using 2 different configurations. So what I'm going to show is about 1 month of tests. He basically making these runs in real time while the HRRR and then the experimental HRRR, essentially version 4, future version 4 of HRRR system are running. So took the ensemble perturbations out of this kind of quasar operation of HRRR and use them in the GSI EnVar using our EnVar code and assimilation reflectivity, and then compare the results with the HRRR version 4 experimental and then operational the HRRR version 3. Sorry, it's as this schematics shows that so now we are, for these extended tests, we are only doing hourly DEA. So basically reflectivity is simulated only a single time. We can continue to do cycling. Here it's just result of the one time. So it's a 1 hour spin up and then do a single time analysis using the GSI hybrid, assimilating both conventional and reflectivity data. So this is the our system. And then, okay, sorry. This is the essentially experimental HRRR version 4, and this one the difference is simply the the reflectivity assimilation. Selective assimilation, the HRRR uses cloud analysis instead of direct assimilation. So the it's still being evaluated. Some initial evaluations using, say, the HRRS scores. It shows that in terms of the reflectivity and for different thresholds, these lines are for different thresholds, and we do see that this is our code or CAPS version, and at least before 8 hours, they actually produce the higher skill score than both the HRRR version 3 and 4. The difference is not that necessarily that big, but it seems consistent. And initially it doesn't match as well, and mostly because the cloud analysis tend to produce a better match of reflectivity with the observation. It's not a kind of it's not at the optimal estimation where it's a weighted average. Okay, so the bias also shows the bias is not worse, and sometimes you get a higher score due to worse bias, but it's not the case, and it's similar to the HRRR version 4. So this, even though we are only doing hourly simulation, not cycled, and then typically our individual case studies and use 15-minute cycle and then at least do the 1 hour radar DA cycling. And also we couple, for our case studies, we couple the GSI EnKF with consistent the GSI EnKF, and here it's coupled with HRRR-. It's also based on GSI, but it's 2 different systems at least, and so you wouldn't say it's completely self-consistent, but and even with this, I think we are achieving the at least somewhat better results than the operational well-tuned system. So this suggests the direct assimilation of reflectivity together with all the other observations, and with it's promising, very promising. I think it's something that we should really push for next generation version of the, say, RRFS. Yeah, all of these tests, just a one case example, the HRRR version 4, basically, the analysis of reflectivity matches the contours very well. Contours is observation, and this is the shading is analysis and contour observation. So analysis, you always get a very good match, especially cloud analysis. But say just 1 hour forecast, and then this is one of 2 test cases, and both are similar. Test cases we did, or Jeff Duda did before his real-time runs, and so it's not just one picked out of cherry picking out of the many cases, just one of 2 that he initially tested. So it shows that after 1 hour, so using cloud analysis, this cluster of storm did not really develop in this the experiment HRRR that uses cloud analysis. I think mainly because like EnKF or EnVar, it has consistent ensemble covariance, and it can produce the consistent perturbations increments in the other temperature, moisture, and other fields, so that can sustain the storms in the initial condition better. And so 6 hours, after 6 hours, for example, this line, the southern part of this line is maintained, and then better than the HRRR experiment HRRR, while this line ahead of it is completely missing, although it's not completely correct in this the CAPS version either, but it at least captured this part of precipitation. All right, so that's kind of the report on our radar DA development and then testing in the GSI framework. It's a EnKF combined with the EN3D-VAR and testing with Wolf and also LAM on the countless grid and using the essentially HRRR physics configuration. If there is the HRRR 5, maybe this can go into HRRR version 5, but next version would be the RRFS. And then I guess we don't know whether the first version of RRFS will be using GSI or using JTTI. Maybe JTTI is mature enough and or development of this is fast enough that the first version of RRFS can use JTTI, but if we can port all these capabilities into JTTI, that's what we hope to do in maybe next round of JTTI. Okay, the next is the brief report on our work supported by the GOES-R risk reduction project, this three-year grant that we had. And this collaboration with also the NSL, Alex Ferraro, and then Ted Manso and Don McGorman, who are the lightning experts. With this GOES-R, and we know that we have GOES 16, 17, and they actually provide a very good coverage of lightning over this, say, in this whole area, and not only just the North America or Kaunas, and the very large area, and it's called a global lightning mapper, and it provides the 20-second the total flash rates every 20 seconds, and the resolution is like about 10 kilometer pixel resolution, and out of this we can derive the total flash rates every minute, for example, over about 10 kilometer pixels, and we call it the flash extend density. And basically all the lightning flashes through the grid, 10 by 10 or so kilometer grid, every grid, and how many flashes go through. And then using that and the early work of Ted Manso's group and developed the observation operator relating this called a flash extend density to total graupel hail mass, integrated graupel hail mass within a 10 by 10 or so kilometer column, and or just simply the volume of graupel within that volume. They find that there's a strong, very good relation between the flash extend density to that. So using such a observation operator, we implemented in both the GSI EnKF and the EN3D-VAR, and then tested with the two cases so far, MCS case and supercell case, and one of the paper is imprint, and another one using the EnVar, it's being reviewed. So again, we can compare 3D-VAR, EnKF, and EN3D-VAR. This is the operator. It's relatively simple, actually pretty linear, although there is the fit is not that tight, and we have tuned these factors. In this case, these were originally developed based on fitting to model simulation of lightning activity. So when it's applied to real GLM, we have to do the calibration, essentially, tune the factors. And then the latest, and before we haven't applied it, is to fit the model forecast FED with the actual observed FED. And we can do a nonlinear fit, and then actually it can, doing that would actually also remove bias associated with the, say, microphysics schemes. And that's the to-do work. With the, say, with this, okay, observation operator of FED implemented in GSI, 3D-VAR, EnKF, and EN3D-VAR in the GSI framework, and then we have tested to say this is resulted with the MCS case, and it shows the comparison of this, the final analysis. It's analyzing lightning flash, but we show the we verify in terms of the reflectivity, which is it's unobserved. We're not assimilating radar data in this case. We can see that actually it can reproduce pretty well the reflectivity field, even though we are only assimilating this two-dimensional FED data. And if we don't do that, and then it's just this is the no DA, and you only capture this just brief the light reflectivity. There's no reflectivity cores inside. And with the radar DA, and the radar DA, then you get the 3-hour forecast. And actually, the overall system is a lot better than this system without FED DA, and it shows up in these ETS neighborhood ETS scores. And you can calculate ETS scores for FED, flash extent density, and then or using the reflectivity for verification. And we see the using FED, actually the the fit is tighter, and the 3DVAR doesn't do a good job because 3DVAR really only update the graupel and nothing else, while the EnKF or EN3DVAR updates all the other variables through the Ensemble covariance. And in this case, for reflectivity, the pure EN3DVAR seems to do a best job. And while for flash extent density, and both EnKF and pure EN3DVAR do a similar job, both are better, much better than if you don't do any lightning DA. The score is just basically the floor. Okay, and then of course the question is what additional value you have if you already have radar data, and do you gain additional benefit? And so we run experiments with the FED only reflect radar data, and then or both, and we find that say in terms of the FED, the forecast, the ETS scores, the assimilating the FED only initially, first hour actually gives better skill, and afterwards they are similar, either with lightning or radar or both. Later time period they are similar, and both cases are all are better than the control, at least like for this case for 2 hours. In terms of reflectivity, assimilating radar is better. The lightning data does improve over the no lightning case. So I think the results are promising, and even though the lightning data is simply 2D data, but it's able to build up the storms and then sustain the impact for 2 or 3 hours, depending on the types of storms, and also depending on the thresholds. If you have like next the RRFS domain, it's supposed to be more like a rep size, and so a lot of it will be over ocean, and probably we hope that the over ocean, since you don't have radar data, then lightning data, because of the very good coverage in the over ocean, it probably should be able to improve. And also for over Atlantic can hopefully also be very beneficial for the hurricane forecasts, although we haven't tried it on the hurricane yet. So that's a part on the lightning, and we have 2 or 3 papers and in different, one published, one under review, and the other maybe two to write up. And this is of course in the GSI, and then we hope that we can move these into JTTI, and then so that move towards the RRFS, and of course, I need support to do that. And so just mentioning JTTI, and so where is it? What's the status of JTTI? I guess a lot of us are wondering. And the first public release of JTTI was like the October 26th, so about 20 days ago. And so we actually have done some work with this first public release of JTTI that actually contains a FA3 LAM interface. And so with this, we moved the radar DA capabilities from the GSI EnVar into JTTI EnVar using all the power transform and stuff, and so quickly tested on this domain. And we actually obtained the reasonable analysis of reflectivity. This is for this particular case, it's simply JTTI 3DVAR analysis of reflectivity. You see the relatively poor background, and then the observation after analysis on this 3-kilometer regional grid, and we obtained this reflectivity that actually matches very well with the observation. And earlier, we were using a pre-release version of JTTI, which did not have FA3 LAM interface. So we did our test on a global grid stretched so that it has about 3-kilometer resolution over counters, and then with that version, we're able to also do the EN3D-VAR using like 30 member of global ensemble with stretched grid. So, and be able to obtain the EN3D-VAR analysis, and that seems also look reasonable. So since they are the JTTI, the variational framework is there, and then after implementing the radar DA capabilities into it, and it's producing at least a reasonable reflectivity analysis. And we're not sure what other variables yet, how the everything works. And okay, yeah, JTTI, of course, you also need a EnKF system to couple with it, and it seems it's LETKF algorithm that's mainly will be supported in the JTTI. Okay, so that's the DA work. Next, so I'm going to report on the real-time forecasts we have been doing for the hazardous weather testbed, spring forecast experiment, and the hydrometeorology testbed, winter experiment, as well as the flash flood and intense rainfall summer experiments. We've been doing the HMT for like maybe six years, and HWT for many years, and then until this year, which we kind of not funded to do. But we have been testing the FE3 for these test beds for several years since the 2017. Yeah, in fact, the 2017 we were supported by the NGTPS program, and to quickly adapt the FE3 global FE3, we implemented Thomson microphysics scheme into the global FE3, and then run in real time during the HWT. And the GFDL was running in microphysics. We were running the Thomson microphysics, and then this is the actually rating, objective rating from the HWT. It shows actually FE3 obtained more of higher 9 or 8 scores than some other say Windows, ARW Windows or NMM, and so it's actually just that first year of just initial trial. I think to help establish the credibility of FE3 for CAM forecasting. Before that, it was considered a global model, and for maybe physics only suitable for global models, and nobody was sure whether it can work at all for the CAM forecast. And then this real-time runs and helped establish at least its credibility. And then the results through the first year's result can be found in this paper. And we actually, we actually compared it with the WRF forecasts run at the same time, and then these like these ETS scores, and these are WRF forecasts. The gray lines ETS scores, and then the blue is the FE3 forecast. And FE3 did not have radar, and the others have radar, so they started with higher score, but the FE3 have to spin up and maybe overshooting somewhat, and then maintain scores. For this low threshold, actually above most of the WRF scores, and then for the high threshold, they are comparable. And bias is not similar bias. And if we looked at spectral, the FE3 actually was able to maintain the more power at the short wavelengths. Although we find out that the CAPS run of ARW was using recommended diffusion coefficient for the experimental HRRR, and that turned out to be higher than the operational HRRR, and the operational HRRR actually maintained the spectral better, and then the CAPS ARW run, but still seems generally power spectrum also looks good. So that's the first year, 2017, and then 2017 we run a single member using just Thomson microphysics and other NYMM and other physics, HRRR-like physics. And the second year, we implemented a whole bunch of other schemes, like NSR scheme and a whole bunch of the PBR schemes. We actually did that and using the GFDL's physics driver interface. And so we were able to run the 10 forecasts for the HWT spring experiment, 2 microphysics, and each combined with 5 PBR schemes, really 3, and then these are scale-aware version versus regular versions. And we reported results on in this GRL paper. I think that it's the first paper reporting on FM the FE3 model forecast with multiple physics for the CAM forecasting. And these are these comparison of scores and for the Thompson microphysics group with different PBR scheme and SL microphysics, different PBR schemes, and the distribution of the so the precipitation intensity compared to observation. This is observation, so the mean of 50% percentile is here. So you can see that they're not too different, but maybe NSL actually a little closer for both the this 99s and then 99.9 the percentile threshold. Like this is more high bias for the Thompson high intensity. It's little surprising for high intensity precipitation. People were thinking SL scheme is more for severe storms, but okay, yeah. And then also the power. Okay, so that's the first 2 years we tried that they were FE3 global FE3 using nested Connors grid, 3 kilometer so Connors grid nested inside of the global the FE3. And of course, the operational the system we're going to use the regional SAR initially called, and then now LAM, FE3 LAM. So that's what we really want to test. So the since late 2019 for the winter experiment of the HMT, and then through the summer of last year, and then now okay, well, and now yeah, we are doing winter experiment forecast for HMT. Yeah, so for the winter experiment of HMT ongoing right now, we're running these 5 forecasts using these physics combinations. We actually had a lot of discussions among EMC and GSR and then the WPC on these configurations, and we end up using like the first 3 members. The physics are actually similar to the expected the RRFS, except that the land surface model. Land surface model we hope to use. I think we want to use the NOAA MP, but it's not tested yet for these combinations, except for the combination of GFS surface and then TKE EDMF, and this has been tested. So in this member we're testing NOAA MP, and this, if it works, and then this probably will become control for the others. And so the first 3 basically test the microphysics, and then for the RFS target, and then the warn and forecast target microphysics, and then the hurricane forecasting system. It's testing the Farrier legal, and so the microphysics. These 3 are actually kind of configurations for the RFS, and then the warn and forecast, and then hurricane analysis forecast system. And these 2, these test the ROC, and the GSR is mainly using ROC, and then this future land surface model. Yeah, so I think these are very good combinations that we want to run and evaluate, and for this winter experiment and through the summer, the FFI intense rainfall forecasts also. For winter, we're running 1 run a week, and from the late November through the early March, and then more runs due to 2 IOP weeks. And so yeah, these 3 kilometer Connors grid, and actually we use the extended Schmidt grid, and then Jimposo's more uniform resolution grid. And again, it's in coordination with EMC, and they are running exactly same grid. And then there's many other levels and grid configurations are the same, and all of these are initialized with the GFS initial condition LBC. We keep them the same and only look at want to look at the physics difference only. Okay, and then just show the test case before we start to run in the early November. This is the test case. It's the Oklahoma ice storm case, where actually OU was shut down for 2 days because of the ice storm. And so this is the precip type forecasts, all of these 5 members, and then using precip type algorithms. And we see that generally there is this freezing rain that cross Oklahoma into Kansas and Texas, and then the sleet mixed sleet rain, sleet inside. And then with these algorithms and the algorithm does tell us that, and then with the Fourier algorithm, it's using a different algorithm that put them apart. But generally, and all these members are predicting, and these are the 36-hour forecast and predicting the freeze and rain and sleet in this across central Oklahoma, and that matches the observation pretty well. So maybe it's partly because of these configuration or streets of physics are reasonably well tested, and they are good combinations. And the interesting question is, Fourier microphysics is relatively, it's a lot simpler and a lot fewer ice species, and we want to see how well it worked for winter. And of course, the experiment is still ongoing, and hopefully in the end we can tell more systematically the relative performance of them. And for this case, if we look at the accumulated precipitation verification, again, they put all the accumulated precipitation in the right place. And the window product that we have created is called a localized probability match, the mean. And this is the probability match mean done in the local domain, so that you don't take like precipitation over the ocean and put it in the maximum location if you're using the global probability matched mean. And actually, if you do that with this global probability match mean, you exaggerate the maximum at the center. You get this 9 point something, and while observed is 4 point something, and the LPM actually gives you very good the maximum in the LPM mean. And then among these, and the NSR gives the best, but yeah, really the difference is probably that statistically significant. Also look at snow accumulation, and the main difference is seems the NSR scheme, and then put more snow inside Oklahoma, where the observed is mostly Panhandle area and New Mexico. Yeah, we were running the FA3 last year, and so last year the report is out, and then there's a limited comparison, and the capsule product was mainly the ensemble mean that was evaluated, which is, we don't think it's the best, and it tends to smooth out since, and then but still it's on par with the other say the FA3 run that EMC did. So that's from last year, and then the performance diagram and shows generally this is cast member, and compared to other the winter the snow forecast product, and some of them were derived from European centers, different algorithms. Generally, as you see this FA3 based forecast, it's close to be unbiased, and then skill score comparable. Okay, for the summer experiment, we run actually 12 members, and then the first 6 using LAM initial condition, and then the next 6 using GEFS perturbed initial condition. So for the last summer's the fair experiment, and unfortunately the code we checked out of the GitHub right before the experiment, and the MYA version contained a bug, and that MYA version was used as control among all the experiments, and that bug actually was very significant. So a lot of these members produce a poor forecast, and like this one used the MYA, and the basically skill score, the land surface condition was just bad, so continually decreased the skill score, while other members are able to have dyno cycles, and then so and this problem has been fixed, and so we are rerunning the bad members, and then hopefully they have a complete good forecast. But yeah, that's also sometimes these bugs and actually show up easily. You can see it. Well, if you actually perform the verifications, you can it will show. All right, so those are the tests, and essentially all with the FE3. Mainly for the HWT and the HMT, and try to use the configurations physics, and then as close as the expected or kind of expected configurations of future operational forecasting systems. So in conclusion, maybe the summary that we have developed these capabilities to directly simulate radar data, both radial velocity and reflectivity, and with the automated like the QC. Actually, we were using CAPS as QC, automated QC for VI, and then pre-processing. So VI is actually also assimilated on the native grid, not the super orbed. And then also GIM ability, the data assimilating capabilities within the GSI framework, and then it's synchronized now with the latest version, and will be checked back into the GitHub, so that can be further tested by the other groups. These capabilities are, well, the system is interfaced with both WRF and then FE3NAM, and tested up to the countless 3 kilometer grids. Generally, the EnKF and then EnVar perform similarly. Sometimes the EnVar better, not always. Okay, and 1 month test and shows that the performance is definitely no worse than the well-tuned the HRRR version 4 that's going into the operation. And most of our tests were using 15 minutes DA cycles, but this real time one was only done in hourly mode. So it's not completely optimal yet, but if we do it a more frequent cycle, coupled with consistent, self-consistent EnKF, we hopefully, well, we should be able to even get even better results, and then test with the real times, mainly with main goal of finding out how the different physics perform relative to each other, and then help us to choose them for different deterministic systems, and also for the see if we needed to use them in to design microphysics ensemble for the RRFS, and that's actually part of the CAPS task for the R2O project. Yeah, we have done some preliminary work and moved the radar capability into the GSI framework, and then produced the reasonable analysis of reflectivity, which is the most difficult part of the problem. There's many people contributing to this, and just to list some of them, and these are NOAA collaborators and then CAPS people. Yeah, thank you. That's all I have. If you have any questions.
Thank you, Dr. Ray. We can open up the rest of the webinar for questions now. If you have any questions, please feel free to type it in the question box.
Let's see, do I see?
There is a tab for questions in the webinar interface if you wanted to look at it, but I can read them out as they come in.
Yeah, I can't find it. I'm not so familiar with. If there's any, if you can read it off.
Sure. Yeah, I don't see any yet. Let's give it another minute.
Maybe too fast.
I see Cliff Mass has a question.
Yeah.
There's a question.
Yeah, can you read it? I can't. I don't know where to find it.
Can we unmute him?
Unmute. Oh, he's speaking.
Let me. He has self-muted. Okay, he has self-muted himself, but meanwhile, we have a question here from Krishna Kumar. He asks, what sort of coordination efforts are you envisioning with the JTTI team, particularly on the implementation of observation operators?
Yes, we have some interactions, and actually we just submitted the JTTI proposal and try to do this, and I did talk to Thomas and then see if we can, if they can be formal collaborators on our proposal, and then I guess they thought they're busy enough, but we are participating in the academy, the JTTI Academy, and then the third one now. We sent in a total of 3 scientists to the JTTI Academy, and through that we had quite a bit of interactions and also obtained access to the experimental prototype system. That's how we started the work. So yeah, so we want to maintain order. we are aware of what work has been done in JTTI, and the NSL group has implemented last year or so. It's simple interpolation of the reflectivity operator into it, and so that's just simple interpolation. Yeah, and yeah, the NSL is also involved, and so we are talking. Yes.
Okay, thank you. I don't see any questions. And Cliff, if you had a question, you're self-muted. You'll have to unmute yourself. Okay, I don't see any more questions. I think we can wrap up the webinar. But Yan, do you have any closing comments?
No, I don't. I joined late. Yeah.
Okay. All right. Thank you, everyone, for joining the webinar today. The recording and the slides for the webinar will be made available on the UFS portal. And with that, we can wrap this up. Stay safe and happy Thanksgiving. All right.
Yeah, thank you, everybody.
Bye-bye.
Thank you.
Okay.
Bye.
Bye-bye.